So Ed here has been, has published a number of articles on the construction of antennas using actually essentially simple techniques, but fantastic amounts of engineering. And he's going to tell us about that, and I'm going to be doing the slides and managing the funny audio here.
Well, then thank you, Ed, for taking the time this evening. We really appreciate you being here with us.
Yeah, you know, if you guys had the meeting Saturday morning, I could drive over there, but Friday night, I haven't done that. That is not easy.
I don't blame you. I don't blame you.
It'll take you 2 hours. My name's Ed Fong, and probably some of you have heard of me or some of you know me. In fact, let me ask for a show of hands. Who's got one of our antennas?
You got over half.
Oh, not bad.
Yeah.
Quite a few. Who's got the triband? Anyone have the triband one?
You have 2.
Oh, wow. Okay. Oh, very good. Very good. So, you know, years ago when we came up with these ideas, and you know, they're pretty standard now. I'm amazed that they're like the front page. It's in the Antenna Compendium. It's the Antenna Classics Handbook by the ARRL, and then our latest one was in last March. It's not on the slide. The triband antenna, and that's been very, very popular. Pretty clever way of doing it. That's a separate talk if you guys want to talk on triband. This is on the dual band. So let's go to the second page. This talk takes about a little under an hour. And again, our connection's really good. So just raise your hands, I'll see it. Or just shout out, the audio is very, very good. And sometimes when we do it, a seminar for Europe or Asia, then it's really tough. It blinks on and off, but this is a very good connection. So this next page here, those are the 2 articles we did. The original one on the base station dual band, and then we did one in a roll-up. And then on the next page, that's our latest one on the triband, last March. That one has been very popular, and again, I'll get into a little bit of it, but that's a separate talk on how we developed that, and actually how many years it took to construct something that was simple, straightforward, low cost, and yet was functional, and with no radials too. And then the next page is the 2 patents, 2 patents that we have on these. And let me tell you a little story on the patents. It was not my idea to patent these, but what we found was after the first one that we didn't patent, a lot of people were building them. They thought it was clever enough to build and sell. So we started catching them on eBay and the websites and things like that. And that was not the intent of it, for somebody else to take. I didn't mind a club building it. They're pretty hard to build, but the clubs can do it. But we found a few manufacturers that wanted to do a little business on the side. Well, that wasn't the intent of the article for you to go build and start selling. So after we started patenting everything. So what I do is, clubs can build it, no problem, but you cannot build these antennas and have an intent to sell and make a profit, because that's for me and my students. My students build these and we pay them, and you know, they get good experience with it. Anyway, okay, next page. We chose a J-pole antenna here, and this was probably in the early 1990s. I was looking at the J-poles. A friend of mine introduced me to them. Dennis Monticelli, who eventually became the Chief Technology Officer at National Semiconductor, and we became we're good friends. But he introduced me to J-pole, and you know, prior to that, you older hams like myself, we grew up with ground planes, right? We all grew up with ground planes. And at the time, they seemed to work okay, and they were easy to build. We would get a SO239 connector, flip it over, either have a copper wire number 12 or something, or even a coat hanger, and put some radios on it. We thought we could hit a repeater, and that was it. Well, it turns out antennas can be a little bit more complex than that. As I went to school and graduate school and went to Cal, and they knew a lot about antennas. A guy named John Winery, I worked under him for a while. He was the guy that, he's passed away now. He was the guy that did all the Apollo, not all the radios, but he did the mathematics for the signal link, what it would take to communicate both video and audio from the moon to the Earth. You know, where you've got losses, how much gain you would need, and all that. So I worked under him. He was very good. And that's where I got a lot of my antenna excitement when he started showing me these really clever designs. But back to the J-pole. I like the J-pole. Has no radials. If you do it right, there's nothing should stick out. That makes it very, very advantageous to putting up in repeater sites. Radios really do harm. They're very tough to maintain after many years. They start falling off. Basically, the wind load is much higher. So I was really intrigued with this. It's got no radios, high wind load, and it also actually gives a better antenna pattern than a ground plane. It actually gives you about 1.5 dB of gain. So I'm not so sure whether you'll notice that or not, but it does give about 1.5 more dB of gain than a ground plane. And it's a very simple explanation that we'll get into in a while. So it's not significant, but it's probably noticeable if you paid attention to it, and certainly measurable, next slide. So anyway, I thought this J-pole thing was just excellent for simplicity. I built some of them, and I started measuring them. Hey, that's pretty good. I like the idea of no radials. Now, the trade-off you get in a J-pole is that you don't have radials, but it's 3/2 wavelengths. In other words, 1.5, I'm sorry, not 3/2, 1.5 quarter wavelengths. In other words, there's 3/4 wavelengths. There's a quarter and a quarter for the half wave, and then you need a quarter wave matching stuff at the bottom. So it's really a 3/4 wave length. While a ground plane is only 1/4, but with radials. So it's quite a bit taller. So what you're trading off is it is taller, gives a little better performance, but not significant. But I think mainly people that operate repeaters and commercial people now like a J-pole because it has no radios. Radios are things sticking out on top of a hill that it's got 100-mile-per-hour winds in the wind, 120-mile-per-hour winds. Experience has shown that they just start blowing over. Well, when I found this thing that Danny Monticelli showed me, he actually showed it to me in a simple twin lead back 30 years ago. So what do you think about this? And I thought it was really nice. Except when I thought, boy, if you could stick it into a PVC pipe, this is a roll-up version, single band. And I said, boy, if you could stick it into a PVC pipe, that makes a pretty nice base station antenna. And that's what we did. That's basically what we did. And then we made a dual band initially. So I thought the simplicity, radios are hard to deal with too. You just got to screw them in, and terrible for portable operation. You got to keep track of it. Sometimes you can make a portable ground plane, put it in an old pack with it, and you have to screw on the radials and things like that. So I really like this idea. We tried them out, and performance I thought was very, very good. Again, it's not significant, but it is about 1.5 dBs better than a ground plane. So let me explain. Well, let me show you the J-pole first. So the next slide. The purpose of this talk was, I'm sure you guys have built J-poles, right? How many of you guys have built J-poles, either copper or twin lead or something? Wow, almost all of you.
Mm-hmm. Twin lead.
How many have you built? How many of you guys have built mine with the dual band? Oh, one. Did you get yours to work?
Did you get it to work, Chris?
Oh, yeah.
You did? Oh,
Was
good.
that the
A
class?
little harder to tune, but yeah, it works great.
It is a little hard. Yeah, it's tricky. You got to tune it a piece at a time. But you can get it. You can get it going. It takes some patience. Oh, good. Then I don't have to sell you one tonight. Anyway, so the next thing I wanted to do by the 1990s was, how do you get UHF on this thing? Because a lot of folks any of you guys drive over to the Dianza swap meet here? You guys ever come on over?
Yeah.
Some? Oh, you guys do? Okay, cool. I'm always there. By the way, do you guys know next month it's going to be at Fry's Electronics? You heard, right?
Yeah. Which one?
That's,
Sunnyvale,
Sunnyvale.
yes.
one off of
That is going to be great.
El Camino.
I was the guy that worked on that got it going and got it all signed off.
It's like where HRO used to
Nice.
I was just totally frustrated with Dianza College.
Yeah.
I don't know whether you guys know this or not. Every time we go, they charge us $2,400, rain or shine. You pay that up front. We
Wow.
thought, even being on public property, we just thought that was terrible. And then they start charging for parking.
Oh.
Yep.
Ridiculous. So I looked into this and we started exploring, and Fry's Electronics came out. We started smooching with them, and we got a contract with them, free
Yay.
of charge.
Nice.
So that's going to be great. The parking lot's huge. It's going to be really fun. If we keep it neat, we'll get it in the future. So we got to make a good showing, be good clientele there, and also go shopping. The way we sold them on is after you can finish with the swap, they'll go shopping at Fry's. That's how we sold them on. So anyway, it should be fun. Anyway, back to the antenna. So anyway, by the 1990s, a lot of these UHF repeaters were coming out. And people were noticing, and most people noticed, hey, my 2-meter antenna, whether it's commercial or whether it's a ground plane or whatever, resonates at UHF. And they can sort of hit repeaters, but quickly you notice it doesn't perform that well. It's, if you actually measure it, if you use a ground plane at 2 meters at UHF resonating at its third harmonic, you get about a 6 to 8 dB loss. It works. So for a repeater, 6 to 8 dB, you'll still hit it for a good repeater, but you start going out distant repeaters, you start talking simplex, and people start noticing it doesn't even perform as well as my rubber duck. And a rubber duck is pretty bad. And people start asking, well, why is that the case? I get really good SWR. And when I looked into it, I said, well, the reason why is whenever you resonate at the third harmonic of any antenna, since it's a vertical, what happens is most of your energy goes up into the sky. So it's not that it's a bad SWR, it isn't a bad SWR, but the energy is going to the wrong place. Because you're trying to talk to someone on Earth, not some satellite or the International Space Station. So it might not be a bad idea if you're using it for satellite, you know, like Oscar 90. You can probably use the same antenna for VHF and UHF and you'll do okay. But not for talking to terrestrially. So when people came up with that, I said, well, let me look into it. So I set out this goal and says, let me see if I can fix this. What would it take to fix this? And you're gonna have to be simple because people were making these antennas, you're not buying them. It had to be simple, reproducible, and still have to be rugged. Still keep the integrity of a J-pole, but could we add UHF to it? So next slide. So again, we couldn't have capacitors. You don't want to have inductors you buy because the variations would be too much. And we tried all types. I played around with this for about, I remember back in, it was about 2000. I started playing with this idea, toying with it, and trying to meet all these requirements. Got low cost, simple for ham to modify, and had to function. Next slide. So next slide is the Smith chart. Basically, all antennas can be sort of explained via a Smith chart one way or another. So I said, well, what does the Smith chart say about antenna design? The main thing you have to remember is that on a Smith chart, the left-hand side is 0 ohms, and the right-hand side is infinity. And as you go clockwise, halfway around the circle, in other words, you start at 0 at the left hand, and you go all the way to the right-hand side where it says infinity, that's a quarter wavelength, λ/4. Or another way of saying it, if you have a quarter wavelength piece of coax, or transmission line, if it's a short on one end, if you go quarter wave, it'll be an open. Or if it's an open on one end, it'll be a short. And that's something that is not intuitive, unless you study real wave theory. I mean, I asked some of my new graduate students this. On the first day of class, almost none of them get that unless they're a ham. Almost none of them. I say, if I short it on one end, what is it in the other? It's a short. No, that's DC. It's a DC short. It's an AC open if it's a quarter wave, and vice versa. If you have a piece of coax that's open on one end, and it's a quarter wave, it's going to be a short. And then I show them with a network analyzer. And that's when I try to separate AC from DC. AC and DC are totally different. One you need a multimeter, and the other one you need some kind of oscilloscope or a network analyzer to understand the impedance. Okay, so we get that concept. Let's go to the next page. So here's a 2-meter J-pole. 2-meter J-pole made of twin lead. Very popular. The only problem now is you can't get a hold of twin lead.
Yeah, that's right.
I have to have all mine special ordered. All our stuff is special ordered from JSC wiring. There's nobody that stocks twin lead. ARRL barely, in fact, they won't stock the 300 ohm stuff. They'll stock the 450 ohm stuff, which they get from JSC wiring. JSC wiring is the only person I know, or place I know of anywhere in the world that makes twin lead. Belden, we talked to the Belden Director of Sales, Western Region Director of Sales, Steve Lamp says, no, we don't make that anymore. I even sent samples to the Chinese and they didn't make it.
Wow.
So the only worldwide manufacturer of twin lead, both 450 ohms and 300 is JSC. And you'll find if you go to ARRL's, it's all JSC. So we went to them and we special order ours with a certain velocity factor and some specs and things like that for transmitting as opposed to transmitting and receiving. Okay, so here in this figure here is a 2-meter J-pole made of twin lead. The dimensions are approximate, depending on the twin lead. It'll vary from as much as 5%. So how does a J-pole actually work? You know, we know how a dipole works. A dipole works by just center feeding it like this, and then when it's center fed, it's about 50 to 75 ohms. If you bend it a little bit, you'll get 50. If it's fully perpendicular to each other, it's probably more like 70 ohms. So here we have a J-pole. So what's the difference? The idea is feeding it from the bottom. See, if you feed it from the center, that's very cumbersome. I mean, mathematically, it's fine. It's still a dipole. But that means you got to get something hooked up in the center. Then you have to have an arm, which means you have to have a tower. A tower will change the pattern, of course. So in terms of mounting a J-pole and a halfway dipole, dipole center fed, oh, it's night and day. Here, we'll show you how to mount this. I have some pictures of it. All it is, everyone has vent pipes up on their roof or something. You just tie to a vent pipe and you're done. You couldn't do that with a dipole. So I think this is a pretty ideal case of having dipole performance without all the rest of the hardware, the tower, the arm, and all this stuff. So how does this work? We have these 37.25. I could have made that 38 inches. That's halfway. And this is a 2-meter example, so that's halfway. But how do you feed the bottom? See, in a regular dipole, in the middle it's about 72 ohms or 70 ohms in that range. That's a low impedance point. You can feed it like this. And your radio is typically 50 ohms. So how do you transform these impedances? Well, the end of a dipole is very high impedance. It's the end of a dipole. It's the highest voltage point. It's the center that's low impedance. So the edges are high impedance. So how are you going to get this high impedance to match? Well, lo and behold, you go back to the Smith chart. You have this bottom piece here, which is the quarter wave. If you short the bottom, if you short it, then a short circuit is 0 ohms. And again, you go back to the Smith chart. A short, 0 ohms, is on the left-hand side of the Smith chart. If you go 180 degrees clockwise, well, that's quarter wave. You go up a quarter wave, what the Smith chart shows you is it's going to be a high impedance, or an open. So that's exactly what you do. Look at this piece here. You short the bottom, and you go up a quarter wave. Well, that's going to be a high impedance, matching the end of the dipole. So this whole thing is vertical now. And you just mount it from the bottom, a couple of clamps, and you're done. Now, you ask, well, why is it, if you add it up, 15.25 inch and 1.25 inches, isn't that 16.5 inches? It is 16.5 inches, but of course, we're used to saying 18 to 19 inches. Well, it's going to be a little shorter because that 18 or 19 inches, that's in air. If you take c, speed of light is equal to f lambda. If you take c as the speed of light of 3 times 10 to the 8th meters per second, 146 megahertz or so, a lambda quarter wave would be about 18, 19 inches. So the key is the c, the speed of light is equal to frequency times lambda. But whenever you're in a dielectric, like twin lead, plastic, or anything like that, it has to slow it down. Water, for example, the speed of light in water, or speed of a wave in water, is about half of what you see in the vacuum, because it's got density. It's the same thing with the twin lead. It's got some density in it, so it slows it down by maybe 10, 15%. So c is equal to f lambda. You're not changing the frequency. That we know, right? You know it doesn't change the frequency, because if you put your handy talkie in there, just because you put in an antenna, it doesn't go 15 kilohertz off. That doesn't happen. So what you must be changing is the speed of light and lambda. So the wavelength actually changes, not the frequency, the wavelength. So you have to compensate for that. So in twin lead, it's a quarter wave is about 16.5 inches in that range. So how do we do this? If I convince you of that, the bottom is going to be 0 ohms. You see spliced and short together. And if you go up a quarter wave, well, according to the Smith chart, it's got to be maybe not infinity, but pretty high, in the thousands of ohms. And that matches the end of the dipole, which is also high impedance, because you're not center feeding it. And if you think this whole thing is continuous, which you would think is continuous impedance, it's 0 ohms at the bottom, and at a quarter wave up, it's in the thousands of ohms. Maybe not infinity, but in RF, thousands of ohms is pretty high. If you believe that, then you have to say, wait, if it's 0 ohms at the bottom and several thousand ohms at the top, it's got to be 50 ohms somewhere, right? Maybe slightly inductive, but something close. If it's short at one end and infinity on the other, come on, it's got to be 50 or close to 50. Well, it turns out that's true. It's at about 1.25 inches though. being 0 ohms at the bottom and a quarter wave up, it's almost infinity. It turns out that 50 ohms or thereabouts, it's about 1 1/4 inch up. So you tap the coax there. And sure enough, go get your Burt watt meter or your SWR analyzer or whatever, sure enough, it takes a dip. And then you take full advantage of that. So how do you make this thing? So these are, it's got to be tens of thousands of these things floating around. Tens of thousands. Not mine, just tens of thousands. But now, you turn to the next slide. When you actually take measurements or even simulate it on EasyNAC or ADS, Fedco, any of these RF pieces of software, the pattern you get, it's a vertical. So the pattern you get there is the fundamental, which we all recognize as a kind of a donut shape 360 degrees pattern. And then if you put the third harmonic in there, and you go measure it with your MFJ or Comet or Bird, it matches both at VHF and UHF. But if you actually look at the pattern through EasyNAC, the azimuth pattern that we're looking at right now, it turns out that it forms these lobes. That's the third harmonic there. It looks, there's like a 4-leaf clover effect. And you can see, a good 75% of it goes up into the sky. And that lobe, that horizontal lobe you see, is about 25%. So only 25% of it ends up staying on Earth. Everything else goes up in the sky. And we used to call them cloud warmers, right? It becomes a cloud warmer. So you want to do something about that. You want to do something about that. And a simple explanation without all the math. Why does it do that? Why does it do that? Well, it's actually pretty simple. If you look back at the previous slide, go back to the previous slide, the half wavelength, I have the 37.25 inches and 38 in that range. Oops, 30 in that range. But if you wanted to do well at UHF, what should it be? Half wave. It should be about 12 inches, not 38 inches. What causes that pattern is that if you wanted that to work well at UHF, you should have cut it off at 12 inches. You should have cut it off, and it works. Oh, if you took that 37 inch and cut it off at 12 inches, it will work great at UHF because it's halfway. It won't work at VHF, right? Unfortunately. But what's happening at UHF with that 37 inches? What's happening is it goes up 12 inches, ideal, but it doesn't stop. It doesn't stop. The current continues to go, and that's what you don't want to do. It starts pulling the wave up because the current didn't stop. That's where those lobes come from. It's because you haven't stopped the current, the drive current, your RF current. If you stop it, then you'll get the nice donut shape. But if you don't, it's going to continue. Well, if it continues, it's vertical, so therefore it's going to pull the wave up. And next page again, that's where you see those 4-leaf clover things coming up. So the idea is, we got to stop it at UHF. If you stop it, then you can get the pattern that we see in the fundamental here, a nice donut pattern, which is what you want. So first of all, let's go to the next page, and let's review some of these J-poles that we looked at. So you can tell I'm kind of obsessed with my life with J-poles, right? I spend a lot of time thinking about all these things, which I shouldn't be. I should be thinking of school. But it's kind of fun. It's kind of fun, and we made a pretty good small business out of it to make money for the students, and then I don't do research grants anymore. I would just do this, and it's enough to make a living and teach. Nice. So let's go through what's out there, the more popular ones. Copper J. Who's got a Copper J?
I do.
Throw it away.
Got 3.
I'll tell you what the problem with it is. It works okay for 2 meters. So I saw like 3 or 4 hands go up. You guys use it on 2 meters, right?
MERS.
Have you ever tried it on UHF? Good. Yes, it's okay for 2 meters. It's all based on the same thing, like that J pole I showed you with twin lead. They're all the same basic architecture. But here, at 2 meters, this concept works good for copper pipes, but not at UHF. And very simple explanation. If you look at these dimensions, they'll be very similar to those of the twin lead. and you can see the J part and all that. But the transmission line part, the J part, in the 2-meter version, in the J part, what determines the width or the distance of the J? It's the plumbing. Right, that right-hand photo, it's that T and that elbow. That determines the distance of the J. And it's okay on 2 meters, because on 2 meters, it should be about 18, 19 inches. And if you go home and measure yours, your copper J, it's about 1.5 to 2 inches, depending on the manufacturer. So quarter wave at 2 meters is 18 inches. A tenth of that will be 1.8 inches. So, usually we use the rule of 1/10. It passes, and it does work. We bought these, they work. The only slight flaw is, on the right-hand side, I showed you how it's coupled. You put an SO239, you solder it, and then how do you jump to the other side? You have to have an exposed piece, and that's where that wire is. It's about 1.5 inch exposed, 90 degrees to your polarization. So how much do you lose? You put it this way, you can put an RF meter there, and it does radiate. Maybe 10, 15, about 15%. 15%, it's hard to measure RF-wise. If you're a mile away trying to listen to someone, you probably wouldn't notice things. But you do lose, because it does start radiating. And not only does it start radiating, it radiates in the wrong polarization. Right? That's obviously horizontal polarization, not vertical. But I think overall it works. I have one. It works. It doesn't work worth darn at UHF. So if anyone claims that this is a dual band antenna, that's where they're wrong. It's a decent 2-meter antenna. The other flaw is pretty expensive these days, copper. Right, 20, 30 years ago, it was worth building, but copper is so expensive. Building one of those, that's $20 in copper right there. You've got to buy one of those 10 feet lengths, that's 20 bucks, maybe a little bit more now. A lot of copper, copper's expensive, but it works. It works, it's clever, whoever came out with it, clever. Next page is the ARRL antenna. This one's not as popular, and it's one step better, I think one step better than the J-pole used at UHF. So they start out with that J-pole, that 57-inch, and then that 19.25 inch in air. And that's the 2-meter version. And of course, they haven't decoupled. Again, at UHF, you would like that radiating section about 12 inches, cut it off, because that's halfway to UHF. But this is clever. It was. What they do is they add a little 6.5 inch piece. What they do is that 6.5 inch piece, that's a quarter wave at UHF in air. This is in air, it's not in plastic. That's a quarter wave. So they add an extra quarter wave, and they use the 19.25 inch piece as the full J-pole at UHF. See, is that clever? Actually, it is pretty clever. It is. The only slight flaw in this is when it goes into one adapter, one SO239 connector. It still sees a low, so the UHF antennas consist of that 19.25 inch and the 6.5 inch. That works. But you haven't decoupled the 57-inch piece. Because remember, it's at its third harmonic. You'll still see a low impedance. So let's say if all things are equal, that means half the power at UHF will go into the VHF portion, and of course the other half will go into the proper section of the 19.25 inch and the 6.5. So that's a good idea, except half of your energy, if you assume all the matching's even, half of the energy of your UHF power went into the VHF part of the antenna. And that part you lose 75%. But at least the other half of your initial power is working well. So that's some good news, some bad news. It works, it's okay, we tried it. Again, if you measure it on UHF, yeah, it's a little weak. You lose, right, as opposed to losing 6 to 8 dB, you probably only lose about 3 dB, 1.5 to 3 dB. So again, measurable, not significant. Then the next page is the one I hope none of you guys have. It's called a Slim Jim. Slim Jim, somehow, I don't know where the rumor got out that this thing gives you 6 dB gain. But you know what the difference is? You see on a Slim Jim and the twin lead, they short the top. Somehow you short the top instead of letting it float, and you get 6 dB. You don't get 6 dB. It works like a standard 2-meter J-pole. All the ones we built, and also Larry Siebig has a website on that. He's passed away now, but his website's still there. He explains there's no way this can get 6 dB gain. It's just a pretty good, if you make it out of twin lead, it's a pretty good VHF antenna, and it works at UHF. Again, it resonates at its third harmonic at about 6 to 8 dB of loss. So it will give reasonable SWR, both VHF and UHF. But to say that it's a dual band, no, and to say it has gain, no. And I don't know, some people just try to pass this off on eBay. 6 dB gain Slim Jim. So think nothing of it. We couldn't show that it gave any gain. So what did I do? Next page here. So after a lot of thought, and it's not like I was tearing my brains out. I would just think about this problem in the evenings. And gee, is there a way we could convert our J-pole and add UHF to it without buying exotic parts? Right? Simple way that you can convert it with a meter, measure things and get VHF and UHF. So this is it. Quite simple when you think about it. We kept the matching stub for VHF and UHF the same because it's not radiating. Whatever matches at VHF, in most cases, will also match at UHF. Because like that stub in the bottom, the 1 1/4 inch and 15 1/4 inch, that's a quarter wave stub. That's a quarter wave stub at VHF, but it's a 3/4 wave stub at UHF. It's the third harmonic. And since it's not radiating, we're not worried about the pattern. So it's okay, it just kind of stays confined in there. At UHF, it does travel an extra half wavelength. So you can say, well, if there's a little bit of loss, it's traveling that extra half wavelength. It should be a quarter wave. But it should be about 5.5 inches if you were to make a UHF matching stub. It should be about 5.5. Rather, it's about 16.5, 3/4 inch. Because you also need that same stub for VHF. But the difference is when it starts radiating, then we start looking at it from a different perspective. When it starts radiating, it wants a half wave at the top, that where I say cut out 1/4 inch knot. At UHF, you want to go up about 11 to 12 inches and cut it off, because that's a half wavelength at UHF. So how do we cut it off? We go back to the stub thing again. Really important to understand fundamentally what the Smith chart says. It says a quarter wave stub. If it's a short at the top, quarter wave down later would be an open. So you've opened it, that 11 1/4 inch. If you put that little stub there at 4 1/4 inches, it's going to look like an open. Only at UHF. It won't look like that at VHF, at resonance, at UHF. And again, you look at this. 4 1/4 inch. Why is it 4 1/4 inch? Shouldn't it be about 5 or 6 inches? That's in air. That's in air. The RG174 has got a velocity factor of 0.66. It's more than 30% shorter than what you think, because it's in a dielectric of some kind. It's not in air. And so after that, we have to add 17 inches, because the 11 1/4, the 4 1/4, and the 17 inches, that's the half wave at 2 meters. So 2 meters, it sees the whole length. But at UHF, it goes up 11 1/4 inches and boom, it's an open circuit, because we put a little quarter wave stub there, shorter than the other end. And sure enough, it works. If I lost everyone, the good thing is I have a camera. No one's asleep. Is no one asleep? No, I think everyone's awake there. So I think everyone's hung on to this. You guys kind of catch on?
Yeah.
Good, okay. And then the next page is, a few years later, one of my students says, the younger kids said, we like to go hiking and all that. How about making a portable version instead of carrying this 5-foot PVC pipe antenna around? And we thought about it. It was just a physical thing. And yeah, we were able to construct one by ordering special twin lead or a coax cable on the bottom. We figured out how to do the cuts with heat shrinkable tubing, and yeah, it's pretty durable. In fact, I can show you some of this stuff. Let's see here.
Where'd it go?
Yeah, here we go. See, so we stuck the whole J-pole just kind of in a PVC pipe,
Oh, yeah.
and this PVC pipe is really, really good. We've tested it in Arizona, in the deserts of Arizona, and this new stuff is really, really good. See, on the roll-up, we have this in a package like this. comes out, and here's the exactly what's in the photo, down to a little hook, a hook on the top. Here is the 18-inch portion. We cover up with heat shrinkable tubing that 4 1/4 inch stub. Here's the 12-inch or 11.5-inch section. And here is the quarter wave section. And then we have a bunch of RG174 with a BNC connector at the end. So what we do provide is we provide a little kit that consists of that antenna and, let's see, let me find it. You buy the kit, and what we do is we have these, we have these cables all made up. They're in 6 feet sections, RG174, with a male and female on each end, so that it acts as a extension, because this is the end of the roll-up. You can just, it's got a male and female, so the cable has a male and female, so you can just plug it in, and then you can add these along. We make them in 6 feet sections, and it's a BNC. By the way, this was not my idea. One of the young hams that I had in my class said, "You got to do this."
Nice.
And we started doing it, and sure enough, it was popular.
Nice.
And then we buy a bunch of these connectors, adapters in the thousands, which is BNC to SMA male, and then we also include a little adapter barrel, which makes it SMA female. This way you can go into your Wusheng radios and your Wusheng and Baofeng radios. So that kind of comes in a little bag and has all the adapters. Great thing to put in your backpack or your emergency go kit because you have all the adapters. So that's the roll-up. That one we published in 2007 in QST. Now, one thing you'll notice is, again, one of the antennas, the base station one, goes into the PVC pipe, and the roll-up just unravels in air. So people, quite a common question is, can we put the roll-up into a PVC pipe to protect it? And the answer is no, you can't, because, again, one is designed to operate in air, and one is designed to operate in PVC pipe. And what does the PVC pipe do? It slows down the speed of light. It's not much. It's like 3-4%. Well, 3 or 4% is a couple of inches. So if you compare the two antennas side by side, the one that's the roll-up, which is designed to operate in air, it's going to be a little bit longer, about 1.5 to 2 inches. And then also the PVC pipe we use is pretty important. We can just send it to bring it over to you guys. You guys have no problem. But people back east, I said, make sure the best one is to go to Lowe's and buy number 23990, 23990 stock number. We found that was the best, had the best RF characteristics.
Huh.
Because you have to remember these PVC pipe manufacturers, they don't have us in mind. Right? It's for gardening, it's not building antennas. So their spec has nothing to do with little metallic particles in there, velocity factor. We have to RF characterize like that. But we do find that the Lowe's one is, it's cheap too. It's really inexpensive. I pay like $230 for 10 feet, which is good for 2 antennas. Has really good characteristics. And not only that, this stuff's supposed to last 30, 40 years out there in the yard. If you look at the material, from what I've heard, it's almost the same material they make the 30-year vinyl windows out of. They treated the plastic with something, because I remember when I was growing up, the stuff would turn yellow right after 3 or 4 years out in the sun, and then it would get real brittle. New stuff doesn't do that. We've had some of these antennas out in repeater sites since 2003 now. They still work. But it's the same thing, you guys have the vinyl double pane windows. I do. They haven't turned yellow. So some clever chemist. Of course, now they're trying to sell you Fibrex, right? A better material. And I thought, wait, my old stuff's still going. They promised me when I changed mine, 30-year windows. Yeah, we've had them for almost 30 years, and they look fine. And they keep on going, oh, we got a better material now, Fibrex. I go, well, Fibrex, why do I need that? Because it'll last 50 years. They go, 50 years? I'm 63. That's right. You think I'm going to really live to 113? No way.
Yes.
So these are just fine. They're always trying to sell me Fibrex. It looks nice, but they're constantly inventing better and newer materials. So anyway, okay, next page. So here's an interesting spectrum photograph taken with an 8591 spectrum analyzer at the university, in fact. See, here's the difference. We took a 2-meter J-pole, it's a standard 2-meter J-pole, measured it, it was like, this is just out in the parking lot, in the clear. We measured it and at UHF, and it's just a relative measurement, made sure the power was just like pretty close to full scale, just so you can see the difference. And then we took that DBJ-1, we'll call it DBJ-1 with the little stub. We tried to make the conditions as exact as possible. Sure enough, you get back about 6 dB. 6 dB, that's 10 dB per division. You get back 6 dB. And you know, it's noticeable. You know, when you talk about 2 or 3 dBs, now 3 dB you can start noticing. By the time you do 6 dB, it's very noticeable. Definitely you can say, hey, that is better than the other. You know, with a standard little handy copy, not taking anything fancy. You know, doesn't need no $50,000 spectrum analyzer to say, hey, there's a difference. No, there's clearly a difference. And that's why these antennas are pretty popular. They're cheap to make, and they work, and they're durable.
Yeah.
And here's a chart. The next one is just actual measurement data. It shows it. It goes through this, like the top one, what is it? Measured relative performance of a dual band at 146 megahertz, 2 meters. 2 meters compared to a mobile antenna, minus 24 dB. That's just a relative measurement. A rubber duck is minus 30, so rubber ducks do lose about 6 dB at VHF. So whatever they tell you, don't use that rubber duck, it's true, it loses about 6 dB. So if you're working through a repeater, you're probably okay. And if you're talking simplex, a few blocks, half a mile, you're okay. But it does lose about 6 dB, that's a lot. Standard J-pole is a little bit better. Again, that's why I was telling you, between a J-pole and a quarter wave, you can measure the difference. You notice it's about 1.3 dB difference. That's hard to hear probably, but it is measurable on the spectrum analyzer, consistently. And if you use our J-pole, which is dual band, it's about that to a VHF J-pole. Whatever the difference is, it's not major, less than a half dB. So that's how it performs at VHF. Well, how about at UHF? Well, at UHF, you get a quarter wave, you get a reference of minus 38.8 dB somewhere. Again, this is out in the parking lot, 50 yards away. We measured, okay, let's leave it there. What happens if we put a rubber duck in the transmitter? Well, rubber ducks at UHF don't lose as much. Because the rubber duck at UHF is already 5 or 6 inches, it's about quarter wave. So you'll find that they're pretty good. In fact, we found some really good rubber ducks that were even very close to that of a quarter wave ground plane. If you're really picky, the comets, what's the other one? Some of the diamonds are very good. If it's a well-designed rubber duck, it can come very close to that of a quarter wave. The reason why is the length. A quarter wave at UHF is 6 inches, and some of these rubber ducks are about 6 or 7 inches. So if you do it right and not screwed up, it can actually perform very, very well. Typically they don't. Typically you lose a couple of dB. So anyway, the standard VHF J-pole, standard VHF J-pole, as you go across this chart here, oh, you're losing 7 dBs here. Not quite, little over 6 dB. So if you use a VHF J-pole at UHF, it shows that you lose about 6 dB on average. It's a lot, that's a lot. If you use our J-pole, it comes right back up. You gain it right back up due to that stuff. So all these equations and simulators and all that, yeah, it shows it's correct. You can actually measure this stuff. If you're doing it all correct, it all should record it. All right, next page, that's our lab. That's our 8597. It's a really cool spectrum analyzer. That's you can pick these up for about $1,500, $2,000 now. Because everyone's gone to this LCD display and all that stuff. All the new stuff, it's all measured. They have not invented a new way to measure S parameters. Internally, the way this measures and a new one measures the same. The display is different. Now they have LCD. This is an old CRT, but you can pick up those CRT now for about $2,000, up to 6 gigs, and really accurate. I mean, that's when we bought it, it was called HP. Now it says Agilent on it, but it's basically the same instrument. They have not changed it. It's Keysight. The newer one is called Keysight, but still the numbers have stayed the same. It's got an 8753D. And the LCD one's obviously lighter, but the actual technique and the way it's measured has stayed the same. So if you guys need a good network analyzer, I say go on eBay. Those are really good. Those are very, very good. That was a workhorse. Still is. Okay, next page. We're almost coming on 45 minutes here. So, the thing that I was curious about is how well does that stub perform? When you just measure the stub on an 8753 network analyzer, here's how it looks. At 445, it's, remember I said it's not infinity? Yeah, it's not infinity, it's where that arrow is, but it's very high impedance, a couple of thousand ohms. And then everywhere else, it just goes all over the place. You don't care about everywhere else, but you certainly wanted it to be very, very high impedance at 445 because you wanted it to decouple. And it does do that. On the next slide, what that is the same stub, but I put my hand around it and I played with it. I want to see how stable it was. And it did what you expect. At 445, it's still very stable because it's at resonance. All the other things, at non-resonance, you put your hands around it, the impedance is going to change, that's okay. But what I was looking for was, does it stay stable at 445? It does. Which means if it rains and snow, it should stay pretty stable. Then the next slide is, how is it at 146? It should look like a piece of wire, an open circuit wire at 146. And that's how it looks like. That's pretty close to an open wire, by the way. It's not infinity, but it's very high impedance. And, let's see, 146 marker of the UHF stub, 445 marker of the open wire. Oh, I'm sorry, no, I'm sorry. This is of an open wire. One point is 146 megahertz, where it's marked is an open wire. Of course, it's an open circuit too, and it's pretty close. At 146 megahertz between the stub and the wire, it's virtually negligible. Physically, they're different, but they're negligible in terms of impedance. And so the next slide is, this thing hangs up really well on your eave of the house. It's end-fed, no radios, very easy to mount. And that's where I think most folks like it. New hams especially. You can mount it on a vent pipe, side of your house. When you have something with radios, it's a lot more difficult to mount. And heavens forbid a dipole, right? To mount a dipole is really, really tough. You need the arm, you need a tower, and it's really a mess. And yet, in the end, it gives halfway performance. So does this. So I think for performance, its simplicity, its cost, pretty good deal, really good deal. The next page is what we offer in a roll-up. You get the roll-up version of that. You get a 6 feet extension, and if you want extra extensions, they're $5. We throw in all the adapters. Great for an emergency kit. And we sell a lot of these for that. Now, next slide is some of my advertisements of future talks. A lot of people say, hey, can you ever get gain out of a J-pole? And I said, you can get gain, and it's not a Slim Jim shorting the little top. You don't get 6 dB, I'll tell you that much. So I looked into this. How hard is it to get gain out of a J-pole? Well, here's one that we patented, a two half wavelength collinear. That's another lecture. We get into how we developed it, and yes, it does give 5 dB gain total over a dipole, and patented, measured. But we can explain that. It takes another hour to how we developed that. And then the next slide is the latest one of how you are able to achieve 220. Because all these things come about because people ask, Ed, can you do this? Ed, can you do this? Ed, can you do this? Well, after a while, Ed gets sick and tired of hearing, Ed, can you do this? And Ed tries to actually do it. And sometimes with some success and sometimes not. But this is a challenging one. Could you add 220 to it, to our already dual band antenna, which by that time there was like 17,000 of them out there. And just, could you add 220? And the guys that were really asking about this was FEMA. Because FEMA started operating a lot of packet on 220, so it wouldn't interfere with the other bands on phone. If you transmit packet on 2 meters and you're trying to receive a 2 meter handy talkie on the field, it just clobbers it. It's transmitting locally. So they did some experiments. If you do it on packet, it doesn't interfere. Of course not, it's at 220. So they asked, could you make one antenna? No radios. We want it idiot proof. We throw it in our band, nothing to put together. And the beauty of it is that they've got 2 meters, 220, 440 radios. You don't have to label the antennas, which all fall off eventually. You can use a magic marker, they wear off. How about one antenna? And if people question the antenna, no, all of them work on all the radios. This is what they want. We want all the antennas to work on all the radios. Idiot-proof. And we want it cheap. And we want 2 meters, 220 and 440. And again, after a lot of thought over the years, and on and off, I said, voila, here it is. What do you think? And they took it and said, you're right, it works. 2 meters, 220, 440. And this is how we did it. If you read the QST article on it, we kind of go through the history of how we developed it. No radios. In quantities, to them, we sell it for $50. I think to your club, low quantities we have to sell for $60 because it is kind of hard to make. But we sell it complete. We ship it with a PVC pipe. And I kind of push it because I think, next page, and you guys got some of these cheap Chinese radios?
Yeah.
The CCRs, cheap Chinese radios? It's what the ARRL calls CCR radios. Well, I got a lot of them. I love to buy these things because when you buy Yaesus, they're $400. When you buy these things, they're $100. And then you get to see how good or how bad they are. Well, there's a lot of them out there. Not a lot, few. The mobiles, like the B-Tech, is a quad band mobile, $128. If you buy it during Christmas time from Amazon, it's $100. That'll go 2 meters, 220, 440, 25 watts, and plus it's a quad band radio because it also covers the 360 to 380 band, which is a ham band in Europe. It's not a ham band here. So here it's a tri-band radio. In Europe, you can use all 4 bands, but it's only $128. And I tell you, I had to buy this just to see how good it was. It's a pretty good radio. It's got a very good front end. I looked into this, who designed it. These were, by the way, all these radios were designed in the USA, back east. It's by a bunch of former General Instruments engineers. General Instruments means they were part of Motorola. In fact, some of them were the guys that worked on, you guys familiar with Max Tracks and radiuses?
Yeah.
Max Track radius. Well, if you look at the front end of the B-Tech UV25, it looks very similar to the Max Track. It was designed by the same engineer. And an easier task to do is buy one of these, measure the standby current. It's virtually identical to a Max Track. It is a very good front-end radio. Plus, it's got beautiful display, color display that you can change. Like if the channel is on, it can turn blue or whatever. If it's on standby, it turns amber. You can program it. It's got 4 lines. I mean, it's very well thought out. It's got 4 lines. You can have all 4. It can be 4 VFOs. You can have 2 VFOs, and the second line would be the alphanumerics. But you can configure it any way you want in different colors. I think we're $128, and it will put out 25 watts. All surface mounts. It's very reliable. We give away these at our we give away at the club all the time. We've given away at least a half a dozen of these. And I have to say, they're pretty good, 200 memories. Now, lower end one, and it's just smaller. It's basically the same architecture, but the display isn't as fancy. It's the QYT one for about $90. Again, that's a quad band radio, tri-band in the US. And then, of course, Baofeng's come out with the tri-band handy-talkie, which I bought one, and it's pretty good. It's like the standard UV5, except it's got the ×3, which gives you 2 meters, 220, and UHF. And it performs quite well. Just if you guys have who has a Baofeng here? You guys have to have a Baofeng, right? You can admit to it. I'm not going to report you. You guys really don't have Baofengs?
Oh, about half of them.
Yeah. Half, okay. We give them, in our club, I buy a bunch, and if you're a new ham, you get one, right?
Nice.
If you buy them by 5, they're only like $21, $22 a piece. So any new ham we get in our club that gets licensed or whatever, we give them a radio.
Nice.
Just to get started, all programmed, right? The whole idea is get it all programmed. They can talk to us, and it gets them on the air.
Yeah.
Great idea.
But they're actually, okay, of the guys that have Baofengs, are you guys happy? Well, let's see a show of hands of the guys that are not happy.
What's the question?
Not happy with
Are you happy
them.
with your Baofeng, or you're not happy? So all hands are not happy.
There's no hands.
No hands. So it must be
hands?
happy.
Yeah, because you were not happy. I said, you're not happy? Then send it here. We'll give it away to someone that would be happy. It's a very good radio, if you really test it. But then you say, well, it can't be that good because the ARRL is not in a QST monthly journal. Well, I looked into why. Because the dolphins are type 90 accepted. That means in the US, it can be used for police and fire. It's fully, I don't know if it's called water, it's not water resistance. It passes the shock test and a bunch of other tests, frequency stability tests. I'm amazed that they can do it for $21, $22. I'm not sure if they're doing it, they could be selling it at a loss. But it meets type 90 acceptance. And we put them on a spectrum
I was
analyzer.
gonna ask about that.
They meet the spec.
Wow.
I mean, are they as good as a Motorola? Maybe not, but they certainly meet the spec by quite a good margin. And so I looked into this. I thought, what's such a good radio for $20, $25? Why isn't it in QST?
Yeah.
Any of you guys know the reason?
Advertisers.
I heard some answer.
Yaesu and ICOM and Kenwood.
Yeah. So did you hear about this, or you just kind of came up with the reasoning?
Reasoning.
Yaesu, ICOM, and Kenwood basically have said, you advertise those at $21, we're out of here for your advertisement.
Yeah.
Which is about well over $250,000 a year. Those three manufacturers, well over $250,000.
Wow.
We're out of here. You're not going to do that. And so they have not. So pretty much, you know, the Baofangs and the BTEC is Baofeng, that's the same company, or QIT is self-promoting, and they're on their own. They will not have, or QST won't accept advertisements from them. So pretty much is what you hear from folks. And in fact, you guys can drive over. In August, at my house, we have a big get-together at the end of summer. Pizza, salad, all you can drink, and then we always have a subject matter, topic. In fact, this year, what it's going to be is we're going to have a spectrum analyzer, watt meter, of course, DC multimeters to measure current drain, spectrum analyzer, and we're going to actually test a bunch of Chinese radios compared to Yaesu, ICOM, Kenwood, and then also some high-end Motorola's. Because I personally want people to see, these are FCC type accepted radios. You just heard bad things because it is the duty of ICOM, Yaesu, and Kenwood to spread bad things about it because their price is incredible. Their price is incredible at $21, $22. I mean, they might be selling at a loss, maybe, I'm not even sure, maybe it costs, but their performance is very good. Their battery life is tremendous. And why is their battery life tremendous? They use a chip that none of the other manufacturers use, the RDA 1845. Complete software-defined VHF, UHF, a commercial chip that's available. And RDA did that because they knew that the commercial market was going to be very big. So why go through a standard architecture and all those transistors, ceramic filters? It just costs too much. If we can spend probably $5 to $6 million developing software-defined radio chip that's specifically designed for VHF, UHF, commercial radios throughout the world, we can sell tens and thousands of these. They did. They got the same group from General Instruments that previously designed a lot of satellite receivers and things like this. Can you design this a radio chip like this using digital signal processing so you don't have external filters? It's just a chip, and it even has all the PLLs in it and everything. And we can really make a killing. They have. I think they have.
Yeah.
So, anyway, that's my pull on them. I mean, with 220 and everything, the prices are tremendous. So can you guys hit some 220 repeaters out where you guys are at?
I don't know.
Or
Not many.
Not many?
No.
Boy, they're all full on this side.
Right. But they're not
Every
over here.
repeater slot here, you can hit a repeater on 220.
Yeah, they're over there, they're not here.
Oh, really interesting. Yeah, here they're all full. Okay, what's on the next page? What's on the next page? You guys are probably getting tired.
Oh, yeah.
Hey, pretty cold night tonight, right?
Yeah.
I think it's pretty cold out there.
I borrowed one of
Here's
those.
another one. Next page is the GP5. Are you guys familiar with the GP5
Yes.
software-defined receiver?
Yes,
Anyone have one?
I borrowed one. Very nice.
Oh, you guys don't have one? Okay. I've introduced these at Pacificon. It's a pretty cool radio that we got involved in, probably 5 or 6 years ago. It's a complete handheld single sideband HF receiver, almost single sideband CW, 200 memories, and really, really nice. We designed a special magnetic antenna for it, so you don't need some long antenna. It intercepts the H field magnetic wave, and it's like a magnetic loop, because it doesn't transmit. That's why you can do that. And you can tune in single sideband, 80 meters and 40 meters. You can go to the CountyCom website, and you see they're about $100, and since I was involved in it, I get them pretty cheap, about $60. They make about 40 on it, but I can sell so many for 60. So if your group wants it, I have a limited supply of these. They're really good radios. You can go to their website, countycom.com, and they have a demo, and it's amazing. It tunes in single sideband, almost like my big receiver. Not quite, but almost. Very, very good. Again, I get a lot of confidence in these digital signal processing chips. Some of them have just done amazing things at super low prices. You know, maybe one of you guys should get one and show the rest of the club. It is quite incredible. Frequency is like right on. You can just tune it down to 10 hertz increments for tuning. But yeah, until you see one, it's seeing the believing. It is amazing what you can do with a DSP chip. So if you guys want them, they're $60. And so the last page, my blurb as a salesman. So my group here, that's how we raise our funds. If you want antennas, the dual band base that we just went over is $30. The roll-up kit, that's the whole kit, is $28. The tri-band base is $60, and we'll deliver that with the PVC pipe. In your case, it's pretty close. I'm sure someone comes over the hill, well, I can drive home. It's a big quantity. We also sell 50 feet coax. The reason why we sell the coax is because a lot of people are requesting it. Not in the coax business. I know when I buy them in hundreds or 200 lots, I can get them for $25. RG8X, the PL259s on each side. On the roll-up, if you want extra extensions, they're $5 each. And then if you need any adapters, a lot of people ask the BNC to female to PL259. That converts the roll-up to standard PL259, $2. With your order, just add $2 to it. So anyway, that's it. Questions? Any questions?
Nice.
Do we have any questions tonight? A lot of good information.
But thank you very much for your attention.
Thank you.
It's pretty cold out there. Cold over here. Hey, so what repeater you guys use?
Well, we have our K6BJ repeater, which is our local repeater. However, we are connected with the Salinas Valley repeater group as well on the 440.
Oh, so there's nothing that so you guys, I'm sure you can hit the 441.3 from where you're at.
Right.
Yeah.
That's ECE.
Yeah,
That's an ECE.
that's an easy one.
Yeah. Then what other ones do you guys use that we can hit from here?
K6FB.
FB?
WR6ABD.
ABD, but.
Oh, you can hit the ABD one.
Right.
And then can you hit the FB one?
Yeah.
Yeah.
FB, okay.
I live in the HOA area, and I actually use my tribander inside the apartment on the top floor, and I've used it with a handy talkie at 5 watts to hit the K6FB on Las Cumbres, no problem.
Oh, wow. Oh, that's pretty good. Yeah, so just make sure it's kind of in the clear. It works best. If it's indoors, it is what it is. But at least don't put it against the wall. I've had people put it against the wall. That really degrades. Try to get it in the clear.
Yeah, it's in an open spot.
I mean, it might look kind of bad, but it works best that way.
It's amazing.
Great. And thank you so much, really.
Thank you. Thank you so much.
We learned a lot.